And the deeper we probe into its mysteries, the more we are forced to ask not just how the universe works, but whether anything is real. Quantum mechanics has transformed the world. We owe most of our amazing technology to its explanations of how extremely small particles behave. But we don't really understand it. In the quantum world, nothing seems to make sense. Reality stops being real. This mystery is our greatest obstacle to unlocking the secrets of the universe. If we can solve it, we may hold the keys to creation itself. Vienna, Austria is arguably the birthplace of quantum mechanics. This is where you will find the leading quantum experimentalist in the world, Professor Anton Zeilinger.
When I first heard of quantum mechanics, when I was a student, I was immediately struck by three things. First, its unbelievable mathematical beauty. Secondly, by the incredible precision to which the predictions work. And thirdly, by the fact that it doesn't make sense.
Quantum mechanics describes the behavior of all the tiny particles that everything is made of. This knowledge has given us computers, nuclear power, satellites, advanced medicine, most of the great leaps forward humanity has taken in the past 100 years. But the quantum world seems to run contrary to everything we know about the laws of nature. Simply put, down where things are very, very small, the universe follows a different set of rules. Consider the phenomenon of quantum non-locality. When two tiny particles instantly share information across vast distances.
If there were quantum dice, it would mean that if I throw one die here, it shows a certain number. The other die thrown at some distant location would show the same number. How can that be? Quantum mechanics describes it very well.
Time and again, Zeilinger has proven that no matter how extreme its predictions, quantum theory works, even though it shouldn't. And perhaps the ultimate proof of just how unsettling quantum mechanics can be is something called the double-slit experiment. It will make you question whether reality exists at all. This simple configuration shoots particles of light called photons, one at a time, through two tiny slits in a screen.
We have a laser which produces light. This light is attenuated such that only one photon at a time emerges. This photon passes through a two-slit assembly, and then we have a camera which registers the pattern behind the two-slit assembly. So what we see is that the photons arrive one by one on the screen, some here, some there, and it looks pretty random.
Since the photons travel one by one, some through this slit, some through that slit, you would expect them to leave a pattern of two stripes on the wall. And you would be wrong. They mysteriously create a band of stripes. This is what you would expect to see if a constant beam of light shined through the two slits. It would spread across the wall like a wave. So how can single bullet-like particles of light create a wave pattern? This could only happen if the particles go through both slits at the same time. In other words, the particle is in two places at once. But strangest of all is what happens when you put detectors next to the slits. When the photons are being watched, the wave pattern disappears. Take away the detectors, and the wave pattern comes back. This suggests that we can change the way reality behaves just by looking at it. Does this mean that reality itself is not real?
The modern answer is that the path taken by the photon is not an element of reality. We are not allowed to talk about the photon passing through this or this slit. Neither are we allowed to say that the photons pass through both slits. All this kind of language is not applicable.
So, do we just keep reaping the benefits from quantum mechanics and accept that deep down, nature plays by a set of rules that will forever remain a mystery?
The interesting message here is that we have quantum physics now around for nearly 100 years, and we are still working at the foundations. And that tells me that when we found it, it will be an absolute revelation. It will be something different from what we have been thinking.
If the quantum theorists are correct, we will never understand the fundamental level of the universe. Our hopes of finding an ultimate theory will fail, and the human race will hit a roadblock it can't break through. But what if they're wrong? What if the truth about what happens deep inside you, me, and everything else in the universe is there, if we're willing to look for it? For most of the 20th century, scientists believed quantum physics could not be explained, that we would just have to accept that we'll never know why things behave as they do down at the deepest levels of existence. But now, a growing band of rebel scientists thinks there may be a logical explanation for quantum weirdness after all, and new hope for revealing the ultimate truth of our universe. The trail begins here, with a drop of silicon. In his Paris laboratory, physicist Yves Coudet and his team conduct an amazing series of experiments. They are observing the behavior of silicon droplets bouncing in lockstep on a vibrating plate.
The liquid of the drop never touches the liquid of the substrate, so they're always separated by air film. And in fact, this is stable. You can keep the drop bouncing on the liquid surface for several days if you wish.
Using a camera that shoots 1,000 frames per second, Coudet has discovered that these droplets mimic behavior seen in the quantum world. And that shouldn't be possible, because the quantum world and the large-scale world play by two different sets of rules. Yet here we see a single droplet moving randomly like a quantum particle, but behaving like a quantum wave. If you watch this carefully, you'll notice that the wave appears to be guiding the droplet. In fact, the wave fields around the droplets develop a memory of the trails they have followed. Despite their random behavior, they follow a small number of paths. Again, this is eerily similar to the behavior of quantum objects. This runs so contrary to popular belief that at first, Coudet refused to believe what he was seeing.
In any physics experiments, you only see what you are prepared to see. Of course, this was very obvious that there was a memory, but it took us some time to realize that it was that we were observing, because you have to adapt to this new idea.
Perhaps most revealing of all, Coudet has reproduced the double-slit experiment using his bouncing silicon droplets. The mystery of quantum mechanics is, how can things like electrons sometimes behave like particles and sometimes behave like waves? Perhaps this is the answer. They are particles and waves. Of course, this system, though small, is not quantum.
Our system is not a model of quantum mechanics, but it is an association of a particle and a wave, and some of its properties are similar to the properties that are observed in quantum mechanics.
Coudet won't claim that his experiments show us what is really happening down at the deepest layers of existence. But this man will. To him, those droplets are more proof that the quantum world makes sense after all, and that reality really exists. Anthony Valentini of Clemson University is a quantum heretic. He loudly proclaims that physics went off the rails in the 1920s when it embraced the doctrine of quantum uncertainty, which says that nothing is real until we look at it. Valentini champions the theory that got left behind. It was created by one of the pillars of early 20th century physics, Louis de Broglie.
Louis de Broglie's original idea is that an electron is both a wave and a particle all the time. It's not the case that, well, sometimes it's a particle, sometimes it's a wave. There is a wave guiding a particle at all times. And de Broglie called this a pilot wave.
In quantum theory, there is something called the probability wave, a purely mathematical object that tells you the chance of finding an electron at any point in space. Pilot wave theory treats this wave as a real physical object.
So a simple analog is a bottle. Someone is on an island and they want to send a message, so they write something on a piece of paper, put it in a bottle, close it, and throw it in the ocean. And water waves simply push the bottle along.
There is a crucial difference between the waves we know and the pilot wave. According to the theory, pilot waves exist in hidden dimensions of space beyond the three we know. If true, this means that contrary to the accepted theory in physics, quantum objects obey the same rules as large objects. They do not exist in two places at once. They are part of the real world.
I think that quantum mechanics itself is not even a candidate for the truth about the microscopic world, because it simply doesn't attempt to describe precisely what the microscopic world is. And the mere fact that there are different theories about what the answer might be doesn't mean that there's no answer. And eventually one of them is found to be the correct one.
To understand how the universe works, we need to unlock why the quantum world is so different from the world we know. It is an unsolved mystery that affects every single person on Earth. And this man thinks he can solve it. The more we understand the inner workings of the universe, the more we humans are rewarded with new medicines, new technologies, and undreamed of improvements in our lives. But some say we're a long way off from unlocking the universe's deepest secrets. We want definitive answers. What we have are mysteries upon mysteries. And one of the greatest mysteries is how the big stuff and the small stuff in the universe fit together. Two well-tested theories describe how matter behaves: relativity theory, which governs the physics of the large, and quantum theory, which describes the very small. If there were a couple, relativity would be a logical, pocket protector wearing engineer who strictly follows the speed limit of light. Quantum theory would be his volatile artist wife who seems to be everywhere at once. On paper, they don't get along. But in the real world, they are a happy pair. And like some real-life odd couples, no one understands why. The mystery boils down to gravity. Gravity dominates the world we know, and thanks to Newton and Einstein, we understand it pretty well. But physicists have no idea what role gravity plays in the quantum realm, or its effect on space and time. If we crack this mystery, we will finally know if it is possible to travel back in time, or through a wormhole. Peter Hoshava has a history of exploring the wild frontier of physics. Now, he's tackling quantum gravity.
So how do you reconcile quantum mechanics and gravity? There are several different ways it can happen. Either quantum mechanics is stronger and wins, and gravity has to be modified, or quantum mechanics has to be modified and gravity stays the same as in Einstein's general relativity.
Peter feels the key is to watch how things change in scale between the upper layers of nature, where gravity holds sway, and the quantum layers down below.
Nature organizes itself in layers of structure, and you see more and more layers as you zoom in and gain a better resolution of how you view the system. It's one of the most important theoretical concepts in modern physics.
To Peter, nature is an archaeological dig that we're slowly excavating layer by layer. Right now, we're only capable of uncovering a small part of the vast and complex ultimate truth. But we can learn a lot by comparing the layers we can see.
In this picture, the two images of Mona Lisa represent the two faces of space-time, space and time. They look the same when we look at it at large scales, but perhaps when we zoom in and look at the system at much smaller scales, it could be that space and time scale in a very different way. This could be the missing piece of the puzzle of quantum gravity.
Peter suspects that as you shrink down to the smallest and deepest level of existence, space begins to stretch at a different rate from time, until they tear apart.
Think of space-time as analogous to this sheet of paper. At macroscopic scales, it's smooth and geometric, two-dimensional. But if you tear the piece of paper into two halves and look at the edge of the paper, zoom in, zoom out, the structure is similar to itself, but only if you stretch in the horizontal direction with a different rate than when you stretch with the vertical direction.
From a distance, the tear looks smooth, but close up, you can see mountains and valleys along the edge. Similarly, space and time seem perfectly joined from a distance, but close up, you can see the separation. Peter thinks this tearing apart of time and space at the microscopic scale is precisely why the strange rules of quantum mechanics emerge. If space and time are unhinged, particles can't be in a specific place at a specific time. Hence, fuzziness and uncertainty. Unraveling the enigma of quantum gravity is a major hurdle in our quest to understand how the universe works. But it shrinks against the magnitude of the biggest mystery facing humanity. 95% of the universe is missing. This woman may know where and what it is. The more we peel away the layers of nature, the more we realize that something is missing. Something big. An enormous chunk of the universe seems to be invisible. We can't see it, hear it, or detect it in any way. But if we want to unlock the secrets of the universe, if we want to advance as a species, we have to find out what and where it is. The universe began with the Big Bang, a shattering explosion of raw energy. That energy burst outward in a mass of superheated plasma, As it cooled, it began to clump together into all the material in the universe, the solids, liquids, and gases that everything is made of. To crack the cosmic code that underlies our universe, we have to understand energy in all its forms. But what if almost 95% of the universe is made of a form of energy we can't see and don't understand? These are the kinds of questions confronted daily in Geneva, Switzerland, the home of the world's largest particle accelerator, the Large Hadron Collider, and also hundreds of physicists. Claire Burridge is one of them, but she's hardly typical. Young, female, and an accomplished figure skater, Claire is trying to solve the vast mystery of the missing universe.
So if we think about the sun, the light from the sun carries energy to us here on Earth, and we can feel the warmth of the sun on our skin on a nice day. But Einstein tells us that what's happening is that energy and mass are the same thing. So in the center of the sun, mass is being turned into energy, and that's what's transmitted by the light here to us on Earth. So the energy from the sun we know and we understand very well, but it seems like there's another form of energy out there in the universe called dark energy that we don't understand at all.
Accepted laws of physics dictate that the expansion of the universe after the Big Bang should be slowing down. But recent astronomical observations have revealed that the expansion is rapidly speeding up. Some unexplained form of energy is pushing galaxies apart.
So at the moment I'm moving forwards even though I'm not doing anything because of the force of gravity. But if I were in space where there are no forces acting on me, I shouldn't be moving at all. If I'm moving forwards, then there has to be something very strange acting on me, and this is what we call dark energy.
How much of the universe is dark energy? Put it this way. Here's the universe. This sliver, 4.6%, is all the matter we can see. Near massless particles called neutrinos take up another 0.4%. We think that something called dark matter accounts for another 23%. Dark energy is the remaining 72% of the mass and energy of the universe. We cannot see it, touch it, taste it, or detect it, but cosmologists are certain it is there. Without dark energy, gravity would cause the universe to collapse in on itself. Claire suspects that dark energy